another session of our online lectures. My name is Mr. Oyebanji I.O. and I will be taking you through types of organic reagents and organic reactions. Of course, organic reagents, as we understand, is a collection of substances that tend to facilitate the conversion of reactants to products. So the process by which reactants will be converted to products is what we refer to as reactions. So if a substance A combines with another substance B to give us substance C, this is referred to as a reaction. Where substance A is a reactant, where substance A and substance B are reactants, and substance C represents the products. So in order for reactants to be converted to products, there must be some specific entity that will allow this process to proceed the way it's supposed to be. And these substances, which are agents of reactions, we call them agents of reactions. So when I bring out the RE from the reaction and I combine it with the agents, it gives me what I refer to as reagents. So when we talk about reagent, the term reagent simply represents reaction agents. So these reaction agents are very important in moving substances from point A to point B, or in changing the overall facets of a reaction into products. So what are these types of organic reagents? The types of organic reagents in organic chemistry are broadly divided into three. We have three types of organic reagents. Three types of organic reagents. We have, number one, we have the free radicals. Number two, we have the electrophiles, that is the electron lovers. And number three, we have the nucleophiles. There are three main types of organic reagents. Number one, we have the free radicals. Number two, we have the electrophiles. And number three, we have the nucleophiles. These three different types of substances that catalyze or allow the homolytic or heterolytic bond cleavage of organic substances are essential for reactions to proceed the way they are. So what are free radicals, electrophiles, and nucleophiles? Before I define the concept of free radicals, electrophiles, and nucleophiles, I'm going to be defining two important concepts. The first one is what I refer to as homolytic bond cleavage. And the second is what I refer to as the heterolytic bond cleavage. When we talk about the word cleavage, so some literatures might use the word fission instead of cleavage. They might call it fission. So we could call this fission. Fission is the opposite of fusion. Fusion means to combine, while fission means to break down. So there are two different types of bond fission, or I call them bond cleavage. So it's either we refer to them as fission or we refer to them as cleavage. Two different types of bond fission, homolytic bond cleavage, and the other is heterolytic bond cleavage. So the type of bond cleavage that occurs in organic reactions or between covalent molecules is what is going to determine the type of organic reagents that we would have. So what is homolytic? Let's look at the breakdown of the two words. We have homo, which means same, and we have lytic. Whenever you hear the word lytic, it comes from the word lysis, L-Y-S-I-S. The word lysis means to break down. So when we hear the word photolysis, it means the breakdown, the utilization of light to break down. When you hear the word heterolysis, It's hetero means disuniform. Lysis means to break down. When we talk about the word hemolysis, hemo means the red blood cell. So lysis means to break down. So applying that concept into what we have here, we have homolytic bond cleavage and we have heterolytic bond cleavage. Almost means same. So homolytic bond cleavage can be illustrated as follows. I have a bond, a covalent bond between chlorine molecule and another chlorine, a chlorine atom and another chlorine atom. These two gives us what we refer to as chlorine molecule. Now, a single bond in chemistry is referred to as consisting of two electrons. So I can say that there are two electrons there. There are two electrons there. So when there is homolytic bond cleavage is a bond cleavage that is uniform. That means the two participating atoms goes away with equal number of electrons. So we have two electrons here in homolytic bond cleavage. An electron comes from this to this, while the other electron comes from this to this. So this results, this is homolytic bond cleavage, this is homolytic bond cleavage. In this homolytic bond cleavage, what do we see? This electron goes to this chlorine, so it comes like this. It gives us a chlorine radical, while this one comes here, giving us another chlorine radical. So when we talk about homolytic bond cleavage, is a type of bond cleavage or a type of bond fusion that results in the formation of free radicals. I repeat, homolytic bond cleavage is the uniform breakdown of a covalent bond that results in the formation of free radicals. So this substance is a free radical. This is another free radical. So basically, as a point of note, homolytic bond cleavage results in the formation of free radical. Now, heterolytic bond cleavage. In an heterolytic bond cleavage, what we observe is that heterolytic bond cleavage results in the formation of electrophiles and nucleophiles. Why? Because the breakdown of the molecule is disuniform. The breakdown of the molecule is not equal. These electrons are shared equally. But here, we could see CH3-Cl. This substance is called methyl, and this is chlorine. This gives us chloromethane. Assuming chlorine and methane, they are sharing two electrons, as we can see from the illustration above. CH3, the methyl group, there's a breakdown. In this breakdown, they are not sharing the electron equally, unlike it will be homolytic. In the case of homolytic, what would you have observed? This will break down, this comes here, this comes here. But rather, in heterolytic bond cleavage, the two electrons go to only one of the participating atoms. And usually, it goes to the atom with the higher number of electronegativity. That means the atom with the more electronegative atom tends to exhibit electron withdrawing effects, while the more electropositive atom tends to exhibit electron donating effect. As we can see here, these two electrons, we have two, the two electrons goes to this chlorine. And when the two electron goes to chlorine, what do we see? We are going to see chlorine becomes negative, N for negative, and the methyl becomes electropositive. So this gives us an electrophile. That means the participating atom that is positive is referred to as the electrophile, while the participating atom that ends up being, we don't use the word positive all the time, we call it electron deficient. Why is it electron deficient? Because the electrons they are sharing, that both of them are supposed to share, that both of the atoms are supposed to enjoy, have been carried away by only one of the participating atoms. So this is electrophile, CH3+, while the chlorine is referred to as the nucleophile. So these reagents now catalyzes different types of organic reaction. For example, we could have free radical substitution reaction, we could have free radical nucleophilic reaction, we could have free radical electrophilic reaction. We could also have electrophilic substitution, we could have nucleophilic substitution reaction, and similarly, we could also have electrophilic substitution reaction. It all depends on the type of reagent that we are utilizing for the reaction. So having illustrated that, there are three different types of organic reagents. We have free radicals, we have electrophiles, we have nucleophiles. As illustrated, free radicals are formed from homolytic bond cleavage. That means, as you can see, there is a uniform breakdown of the participating atom, while heterolytic bond cleavage results in the formation of electrophile as well as nucleophile. So having illustrated that, so let's now let's give further examples of free radicals and defining free radicals. So as you can see here, free radicals here, they are atoms with unpaired electrons. So we say free radicals are atoms with unpaired electrons. So as you can see here, if chlorine splits, it gives us chlorine radical plus another chlorine radical. If bromine undergoes a breakdown, it gives us bromine radical plus bromine radical. If I have iodine splitting down, iodine molecule to give us iodine radical plus iodine radical. Similarly, I could have, if possible, we have homolytic bond cleavage, we could have methyl radical plus chlorine radical, provided that the bond cleavage is homolytic. While if the bond cleavage is not homolytic, then we are going to be having nucleophiles and electrophiles. So these are free radicals. Examples: chlorine radical, bromine radical, iodine radical, methyl radical. What are the examples of electrophiles? Now we move to electrophiles. So a simple, easier way of identifying your free radicals is by taking note of the fact that they are usually molecules with a dot somewhere on top of the molecule. As you can see, there's a dot here, there's a dot here, there's another dot here, and there's another dot here. So once you see molecules carrying something like a dot or carrying an unpaired electron, you know that you are talking about free radicals. Now looking at electrophiles, of course, I remember I said electrophiles are electron deficient species. They are electron deficient species that attack electron rich centers, just like the poor begin to attack the rich. So we have the electron deficient species. They don't have their electron have been taken away from them, so they are always looking for ways to get back their electron. So that is what we observe here. So let's look at this. We have, as I illustrated, CH3, that's Cl. The two electrons are coming to chlorine, so chlorine becomes negative and this becomes positive. So we could have CH3 plus, we could have R plus, we could have NH3 plus, NH4 plus, you could have H plus, you could have H, okay, you could have H plus, you could have NH4 plus. So once the charge is positive, then it is more likely going to be an electrophile. However, electrophiles are not only limited to charged molecules. There are molecules that you cannot see the symbol of plus on them, yet these molecules are electrophiles. So in that case, we begin to apply the concept of electron deficiency. We say that the molecules are electron deficient. And what do we mean by that? We look at a chemical bond between boron and fluorine. between boron and fluorine. In the case of boron and fluorine, each of these bonds represents 2 electrons, 2 electrons, and 2 electrons. Which means that by the time we look at the total electrons surrounding our bromine, we have 6 electrons. Whereas, when atoms undergo chemical bonding, from your normal elementary chemistry, you are aware that atoms are supposed to have 8 electrons. But rather here, boron is having 6 electrons. So we can consider this boron to be electron deficient. We can consider the boron to be electron deficient. And so because the boron in boron trifluoride is electron deficient, their BF3 is going to be what? An electrophile. Electrophiles are what? Electron deficient species. So they could be charged molecules or they could be groups of atoms. So those are electrophiles. Another example is aluminium trichloride. Example, boron trichloride. Example could be aluminium trifluoride. All the tri-halides of the 3 elements are regarded to be electrophiles, and they are also called Lewis acids. So, having discussed that, finally we discuss about the nucleophiles. We will be rounding up by talking about the nucleophiles. Now, when we describe electrophiles to be electron deficient, we will be describing our nucleophiles as electron-rich species. I repeat, electrophiles are electron deficient species that attack electron-rich centers, while nucleophiles are electron-rich species that attack electron deficient centers. So most likely, an electrophile is likely to attack a nucleophile, while a nucleophile is likely to attack an electrophile in the course of an organic reaction. So let's see what I'm trying to illustrate. I have examples of nucleophiles. So nucleophiles, they are what? Electron-rich. They are electron-rich species that attack electron deficient centers. Example, Cl minus, NO2 minus, SO42 minus, NO3 minus. We could have HSO3 minus. So when the charge on them is negative, then they are more likely to be nucleophiles. However, it is not only the charge that tells us about the nucleophile. We could also have electron-rich species. So other electron-rich species that are neutral molecules that are nucleophiles include your water. We could be talking about your ammonia. We could be talking about SO2. All these are examples of nucleophile. So, as a recap of our lecture, today we discussed about the types of organic reagents. We have 3 of them. We have the free radicals, we have the electrophiles, and we have the nucleophiles. Free radicals are molecules with unpaired electrons formed as a result of homolytic bond cleavage, while electrophiles are electron deficient species that attack electron-rich centers, and they are formed as a result of heterolytic bond cleavage, while nucleophiles are electron-rich. Electrophiles are electron deficient. Nucleophiles are electron-rich species that attack electron deficient centers in a chemical reaction. They may be negatively charged or they are neutral molecule. I hope you enjoyed the class. Please ensure to like, subscribe, and drop your comment. Till we meet in our next session, enjoy an amazing day. Cheers.